Welcome to all of you. In this lecture, we are going to study two topics, step index fibers, under which the single mode fibers and the multimode fibers, and one more topic is the graded index fibers. Let us start with the step index fibers. So index here stands for the refractive index. If the refractive index in the optical fiber is varying in the form of the step, such fibers we call as the step index fibers. Let us have a better understanding of this from this diagram. So this is the core of the optical fiber having the constant refractive index N1, and this is the cladding part of the optical fiber having the refractive index N2. Core will have the higher refractive index and cladding will have the lower refractive index. Now this refractive index is being represented over here. This is the core region of the refractive index, that is the higher, and this is the cladding part of the refractive index which is lower than that of the core. Now if you observe the variation of this representation, it is in the step manner. Therefore this is called the step index fibers. Now the refractive index is going to have a stepwise change that is given by n of r is equal to n1 for r less than a representing the core, n2 for r greater than or equal to a representing the cladding. There are two types of step index fiber. One is the single mode step index fiber. Second one is multi-mode step index fiber. So this diagram is going to indicate a typical multi-mode step index fiber, and this diagram is going to indicate a typical single mode step index fiber. Let us start with the single mode step index fiber, also known as the mono mode step index fiber. And this one is going to represent a typical single mode step index fiber. Now this refractive index is going to vary in the form of the step. Therefore, the term step index fiber has satisfied. Now coming to the term the single mode. As the name itself is going to indicate, only one ray of light is going to propagate through this fiber. So typically it is of He11. Therefore, this is known as the single mode fiber. Because of that reason only, it is going to have the lesser diameter of the core. Let's have more details about this single mode step index fiber. Smaller core diameter, that is 2 micrometer to 10 micrometer. Low intermodal dispersion. Intermodal dispersion stands for broadening of the transmitted light pulses. Since only one light pulse is being transmitted through the core, the intermodal dispersion is quite less in this case. Since the core diameter is quite less, coupling of the optical sources like LED is quite difficult in this case. They exhibit greatest transmission bandwidths and the lowest losses of the fiber transmission media. Then they are future proof. Future proof in the sense, as the time lapses, requirements of the bandwidth may keep increasing. In spite of that also, these optical fibers can be used for increased bandwidth services. It is not required to replace it again and again. Therefore, we call them as the future proof. So they are compatible with the latest technologies of the optical fiber. That is what developing integrated optics technology. Now coming to the multimode step index fiber. Now the concept of step index remains same here also. Again, this refractive index representation varying in the step form. Therefore, the term step index is going to remain as it is. Now the term multimode, as the name itself is going to indicate, so several rays can be propagated through the optical core. Therefore, the term multimode is being used. Since several rays are required to be transmitted, the core diameter is much higher in this case. Let's have more details about this multimode step index fiber. The core diameter is of around 50 micrometer or greater than that. Because of this higher diameter of the core, it is possible to couple the optical sources like LED very easily to this core. So dispersion loss is slightly higher because of several rays are being propagated over here. Therefore, there will be a difference in the group velocities, because of which it causes the dispersion losses. And finally, lower tolerance requirements on the fiber connectors. Let us have a comparison of single mode fiber as well as multimode fiber with a set of parameters. The first one, the core diameter. In case of single mode, it is small, varying from 2 to 10 micrometer. In case of multimode, it is around 50 micrometer or greater than that. The number of modes, only one ray is being propagated here, therefore it is one or single ray path, and in this one several, therefore it is many. Optical sources, so coupling of the sources like LED is quite difficult in this case due to the lower core diameter, whereas in case of multimode the core diameter is bigger, therefore coupling of the optical sources like LED is quite efficient. Optical source coupling requires a lot of effort, so here it can be easily and efficiently coupled. Intermodal dispersion, so single ray, therefore it is quite less. Here several rays, therefore it is high. Bandwidth advantages, good for higher bandwidth application, and this one good for low bandwidth applications. Let us go through a problem related to the step index fiber. The problem statement: a multimode step index fiber with a core diameter of 80 micrometer and a relative index difference of 1.5% is operating at a wavelength of 0.85 micrometer. If the core refractive index is 1.48, estimate first one, the normalized frequency for the fiber. Second one, the number of guided modes. So let us identify the given parameters first. So given core diameter, that's the core diameter, 80 micrometer is being given. So from this core diameter we can identify the radius of the core. The radius of the core is given by A, that will become 40 micrometer. So 50% of this diameter is the radius, therefore radius becomes 40 micrometer. The refractive index difference, so that is the relative refractive index difference is 1.5%. So that is represented by delta, that is equal to 1.5%. The core refractive index is 1.48. So core is represented by N1, the core refractive index, therefore it is 1.48. The wavelength is given by the lambda, so that is equal to 0.85 micrometer, that has been taken here. Now let us start with the solution. First we have to identify the normalized frequency of the fiber. So the normalized frequency of the fiber is given by, and in this case it is a multimode. So it is V approximately equal to 2 pi by lambda A N1 of 2 delta to the power of half. So one on the right hand side, all these parameters are known to us. So lambda is the wavelength, it is already available for us. A is the radius, so that is available. N1 is the refractive index, so that is also available. And delta is the relative index difference, so that is also available. So let us substitute it. So 2 pi and then A value is equal to 40 micrometer. Then N1 is 1.48, lambda is 0.85 into 10 to the power of minus 6. Then 2 into delta is 0.015. Now resolving this, we will get the value of 75.8. Calculating the second parameter. Second parameter is number of guided modes we need to identify. Now the number of guided modes is given by ms is equal to V square divided by 2. So V just now we have calculated, and this is what the V square value 5745.6, and then the 2 is retained as it is. So by this we get 2873 as the answer. Now approximating these two values, we can say that the fiber has a normalized frequency of approximately 76 rounded off to the next value. So giving nearly around 3000 guided modes. Now let us get into the graded index fibers. So these graded index fibers can be considered as a special case of multi-mode step index fibers. Special case. So what it is going to have is, so this is a typical representation of the graded index fiber and the ray traveling through it. And with respect to refractive index, we can observe that the cladding is have a constant refractive index, whereas the core is not having a constant refractive index. Rather, it is going to vary in such a way that at the core axis it will have the highest refractive index, and which will decrease towards the cladding. So that means it will have a parabolic shape of refractive index. Now coming to how exactly it is going to work like. Consider this diagram. So this diagram is indicating only core region of the optical fiber. So here we can observe that there is no one refractive index present. So this line is going to indicate the axis of the optical fiber, and other dashed lines are going to indicate the regions with varying refractive index within the core. So that means this particular region is with N1, and then N2, N3 up to N6 is being represented here. So that means within the core itself there are regions of variation of refractive index. So in this example it is taken from the refractive indices varying from N1 to N6, where N1 is greater than N2, greater than N3, greater than N4, greater than N5, and greater than N6. And for and all these refractive indices are always greater than that of the cladding refractive index. Therefore, here one ray has been represented which enters into the core of the optical fiber, and then it will get totally internal reflected within the core region. So in the previous cases what we had gone through, in those cases the ray of light reaches to the core cladding interface, and in that interface it will get total internal reflection. Whereas in case of gradient index fiber, the criteria is quite different. So it has not at all reached to the core cladding interface, rather it has got total internal reflection within the core region. So this is the reason, because so there are several variations in the refractive index within the core. So based on the type of ray and other criteria, that ray of light may get total internal reflection somewhere within the core or at the core cladding interface. So here we can observe a total 6 rays. Considering only the top part, here we can observe that this one is getting total internal reflection very early in the core region, and this is little bit later, and one more at the core cladding interface. Similarly, it has been shown at the bottom region also. That means these several ways, when they are propagating together, they are going to get total internal reflection either within the core region due to the variation in the refractive indices, or based on the type of the ray and other criteria, they may also get total internal reflection at the core cladding interface. That means the refractive index of the core is not linear, it will keep varying, but these different refractive index within the core are always greater than that of the cladding value. Now it is represented by n of r is equal to n1 of 1 minus 2 delta of r divided by a to the power of alpha whole to the power of 1 by 2 for r less than a, that is representing for the core, and then for cladding it is n1 into 1 minus 2 delta to the power of 1 by 2, that is equal to n2 for r greater than or equal to a. In this representation, delta is the refractive index difference and alpha is the profile parameter. Now, based on the value of alpha, the shape of the core refractive index is going to vary. That is being represented in this diagram. If alpha is equal to 1, the shape of the refractive index in the core is going to vary in the form of a triangle. If it is 2, then it's a parabolic structure, and similarly if it is infinite, then it will have a step-like structure. So this is a case where the skew rays are being traveled over the within the graded index fiber. So for the sake of remembrance, skew rays will never cross the center axis of the core. So that's what the skew rays. So by moving in this fashion only, so they will travel further. So in this case, we can observe that this skew ray has never reached the core cladding interface. Rather, it has got total internal reflection within the optical core itself. Now let us go through a few more problems. Now the problem statement. So this is related to the graded index fiber. A graded index fiber has a core with parabolic refractive index profile which has a diameter of 50 micrometer. The fiber has a numerical aperture of 0.2. Estimate the total number of guided modes propagating in the fiber when it is operating at the wavelength of 1 micrometer. So identify the given parameters. The core diameter is given as the 50 micrometer. From this we can identify the radius of the core, that is equal to 25 micrometer. The numerical aperture is given 0.2. So note down that 0.2. And then the wavelength of the light is being given, that is 1 micrometer. Therefore lambda is equal to 1 micrometer. So now let us start the calculation. So normalized frequency is given by V is equal to 2.5 lambda A of numerical aperture. Substitute 2 pi into A value is radius 25 micrometer. Numerical aperture is 0.2. Lambda is 1 micrometer. By resolving this, we get 31.4. Now getting into the mode volume calculation. That's what the required concept. Mode volume we need to calculate. For graded index fiber, it is given by mg is equal to v square divided by 4. We just now calculated. We can identify g square. It is 986, and then divide it by 4. We get 247. Therefore, we have calculated the mode volume. Hence, the fiber supports approximately 247 guided modes. One more problem. The problem statement. Estimate the maximum core diameter from an optical fiber with relative refractive index difference of 1.5% and core refractive index of 1.48 for a single mode operation. It may be assumed that the fiber is operating at the wavelength of 0.85 micrometer. Further, estimate the new maximum core diameter for single mode operation when the relative index difference is reduced by the factor of 10. Consider the normalized frequency P is equal to 2.4. So let us note down the given parameters. So the core refractive index N1 is equal to 1.48. Relative index difference is given, that is delta is equal to 1.5%. Then wavelength is given, lambda is equal to 0.85 micrometer. The normalized frequency V is given, that is equal to 2.4. And these parameters are applicable with respect to the single mode of operation. Now we are going to have the formula for the normalized frequency, that is V is equal to, that's the formula. By rearranging that formula, we can identify the representation for radius of the fiber, that is A is equal to V lambda divided by 2 pi n1 into 2 delta to the power of 1 by 2. So we know all the parameters of the right hand side, make the substitution. So V is 2.4, then lambda is 0.85 micrometer, then 2 pi n1, the refractive index is equal to 1.48 and delta is equal to 1.5%. 2 delta will become 0.03 to the power of half. By solving this, we will get the answer of 1.3 micrometer. That means the radius of the fiber for these parameters is going to be 1.3 micrometer. Now calculating the diameter for this, exactly double to this is the diameter. Therefore, 2.6 micrometer is going to be the diameter for the single mode operation. Now the continued question. So with a reduced relative refractive index by the value of 10, then we need to calculate the radius. So reduction in the relative refractive index in the sense, so that corresponds to the value delta. So now delta is 1.5%. So reducing this by the factor of 10 in the sense, it is 1.5 divided by 10. So it will give us the value 0.15%. Now for the relative refractive index difference of 0.15%, we need to calculate the radius of the fiber. So same formula, only the parameter delta is going to change, all other parameters remains the same. Therefore the substitution has been done over here. Now the delta is going to be 0.003 to the power of half is going to happen. So now by substituting and simplifying, we will get the answer as 0.4 micrometer. So this is the radius of the fiber. Corresponding diameter will be exactly double of this one, that is equal to 0.8 micrometer. So we can identify that. So changes in the relative refractive index will also causes variation in the core diameter. Now let us get into one more problem which is asked in the previous examination, that is August-September 2020. The problem statement: find numerical aperture and number of propagation modes for a step index fiber with indices 1.5 and 1.48 with core radius 25 micrometer. If the wavelength of optical signal propagation in the fiber is 1300 nanometer. So we need to identify the numerical aperture and number of propagation modes, and consideration is it's a step index fiber. Note on the given parameters. So refractive index of the core is 1.5. Refractive index of the cladding, that is N2, is equal to 1.48. Core radius directly given, A is equal to 25 micrometer, and wavelength of the optical signal is also given, that is equal to 1300 nanometer. Right, so first let us calculate the numerical aperture. The numerical aperture is given by the difference of the refractive indices. So numerical aperture is equal to n1 square minus n2 square whole to the power of half. So we know n1 and n2, substituted, then we are going to have the answer 0.244. Then let us calculate the V, so that by making use of V, we can calculate the number of modes. So V is equal to 2 pi by lambda A into numerical aperture. Then 2 pi, the radius is 25 micrometer, and then numerical aperture is just our calculated 0.244, and then lambda is 1300 nanometer. So by calculating this, we get 45.11. Now calculate the number of modes. So m is equal to v square by 2. So v just now calculated. So 45.11 square divided by 2. By solving this, we are going to get the answer 1018. So the number of modes is approximately equal to 1018. 0.18. Thanks for joining.